All right, good. So yesterday we wrote down the definition of being asymptotically the same. So again, two sequences or two functions are asymptotically the same if they have the same long run behavior. And mathematically, it's when the limit of the ratio is 1. This means that, again, in a long run, as n goes to infinity, where is it? In a long run, an and b sub n become the same. And we saw a graph of sine of 1 over n and 1 over n, this problem. And we saw that for n being like 1, 2, 3, 4, 5, the two sequences are very different. But when n gets big, the graph of these two functions is almost the same. You can't make a distinction between the two. And the limit comparison test, which is such a beautiful test. It's just so freaking cool, man. This thing says that if two sequences behave the same way in a long run, and we care about long run because these are infinite series. If two sequences behave the same way in a long run, then their sum behaves the same way, meaning that if one converges, the other also converges. Okay, so let's see a bunch of examples. Again, this test is the easiest test. I hope the notations don't freak you out. As long as you can overcome the notation phobia, you'll be fine. Okay.
Professor, really quickly,
Yeah.
are you limited to specific series on which you can use the comparison test?
Let's see. Well, the comparison tests, they work all the time. They should work for any series. It's just that sometimes we have a hard time coming up with a sequence that is asymptotically the same as another sequence. Sometimes it's difficult, not often, but sometimes, and we're gonna see examples. But this test is meant for series that look like crap. Here is an example of such series. And going from 1 to infinity of, let's say we have 10 n to the power of 4 plus cosine of n plus, let's say, 3 to the n. It already looks horrible, doesn't it? And say the denominator of that fraction is, let's go crazy, 100 n to the power of 10 plus, say, 5 to the n plus ln n. Yep. Looks like crap indeed. I mean, what are you gonna do? Nth term test? Even the nth term test is obnoxious. Taking the limit of this as n goes to infinity. I mean, we could do that quickly. We could do that fairly quickly, but integral test? Hell no. Who wants to do integral tests on this one? We always want to avoid integral tests. So the next test would be basic comparison. No, I don't want to do that. Coming up with the guessing, first of all, what happens here is okay. I mean, we can guess, but coming up with a sequence that satisfies a certain inequality, no, thank you. The limit comparison is the best because we can come up with a sequence that is asymptotically the same as this sequence. Okay, so Yeah, here our a sub n is this whole thing, guys. This is our a sub n. And again, we're gonna do this in steps. Step one, we have to do these in steps. Step one, these steps are, trust me, they are really easy comparing to other tests. You're going to find a sequence b sub n such that a sub n is asymptotically the same as b sub n. This is the very easy part. All you have to do is ignore or just take dominant terms, ignore non-dominant terms. This is our sequence a sub n. Gonna copy that down. Okay, this is the easiest part. All you have to do is take the term that dominates on top and term that dominates in the bottom. Okay, and you want to go with the order of functions that we were talking about yesterday. The dominance, the order of dominance. Again, ln n is the least powerful one. And then we have power functions. And then we have exponential functions. So r to the n. And then we have n factorial, more dominant than exponential, and then n to the n is the most dominant. Okay, because for n to the n, both base and exponents grow. Okay, so look at the numerator. Okay, and by the way, cosine n, just ask yourself, does that grow? Cosine n doesn't even grow, guys. As n gets big, this thing just fluctuates between -1 and 1. So I'm going to mention that over here, actually. Select. Yeah, so here cosine n and sine n do not grow to infinity. Okay, they don't dominate at all. They just do nothing in terms of growth. All right, so on the numerator then, this is not dominant. Here, this is not dominant. Let me just cross that out. Cross the non-dominant terms, not dominant. So you have the option between 10 n to the 4 and 3 to the n, which is more powerful, that or that? And again, this should be obvious. 3 to the n is more dominant, so that you just cross out. That doesn't dominate. In the denominator, ln n is the least powerful. Ignore that. And then you have a power function, 100 n to the 10 and 5 to the n. That doesn't dominate. 5 to the n dominates. So this is asymptotically the same as 3 to the n over 5 to the n. And that becomes your sequence b sub n. We are talking about a geometric sequence, guys. This is now a geometric sequence. Okay, and we can easily determine what happens to a geometric series. So step 2. This is the asymptotic statement. Okay, and for this part, all you have to do, you don't have to do any math. I don't want you to do any math. I don't want you to do any algebra. I don't want you to do any calculus. Just write down the limit of a sub n to b sub n is equal to 1. Just write this down. You don't have to prove it. You don't have to do anything. Just write this down. That's it. Okay, do not evaluate the limit. Because we know that the limit is already 1. since these two sequences behave the same way. Okay, so I mean it sounds weird. You just have to write this down. Okay, and then next step, you're going to determine what happens to the series of B sub n. Okay, because we're comparing our series to this series. So the summation of B sub n is, again, here n goes from 1 to infinity. It's 3 to the n over 5 to the n. All right, look, these are both exponential. These are both geometric. So you can write that as a single base 3 over 5 to the power of n. And that tells you what the common ratio is. So what do you think? Is this convergent or divergent?
Convergent.
This is convergent because it's a geometric series with ratio being 3/5. Guys, give me 1 second, please. 1 second. All right. Yeah, so this converges because it is a geometric series with absolute value of r less than 1. Or you can just say r between -1 and 1. Okay, you don't even have to do absolute value. And the reason for that is because this is just a positive term series. It's a positive term series. R is between 0 and 1. So that's it. That gives us our conclusion. That's the last step. And here you say that, I don't need the indices, the sum a sub n, I'm not even gonna copy the sum. I'm not gonna write it down, but I could just copy and paste. Yeah, so this converges also. Converges by limit comparison test, LCT limit comparison test. That's what it stands for. Seriously, this is very easy. Comparing to other tests, much easier. All right. Yeah. I mean, just think about it for a second. We have two functions. We're gonna look at it from a continuous perspective, but we have two functions. Let's say this is f of n, and let's say we have another function g of n. G of n is, let's say, so what happens is that as n increases or as x increases, let me just call it x. We have f of x and we have g of x. As x increases, what happens is that the two functions basically behave the same way. They approach one another. Okay, g of x. All right, and if you look at the integral under these curves, if the integral under g of x is convergent, if this is convergent, then this integral has to converge also. Okay, because the difference between the two integrals is basically this much. This area and that area is finite. Okay. Just imagine if this integral is 10, okay? And this area is like, let's say 5, then this area is 15. One converges, the other has to converge. All right, any questions? So just take dominant, if you have a rational, if we have a rational sequence, this is not a rational sequence, a sequence in fraction form, then just take dominant terms on top and bottom, and you get a much simpler sequence. Dominant terms, okay? Next example, let's do something with sine of 1 over n. Let's say we have this series, n sine 1 over n squared. Okay, so every time you see a sine of 1 over n, 1 over n squared, sine of 1 over n cubed, sine of 1 over anything, then you do want to do a limit comparison test, okay? Because we have an asymptotic identity for sine of 1 over n. Guys, we know that sine of 1 over n is asymptotically the same as 1 over n. Okay? Yeah, if you want to expand this for a little bit, here, let me just expand. So if I plug 1 in, I just get sine of 1. Next term will be 1/2 sine 1/2, 1/2 squared. So that's 1/4. Next one will be 1/3 sine of 1/9, and so on. We want to know if this thing converges or diverges. But again, you see sine of 1 over something, limit comparison, because sine of 1 over n compares to 1 over n. Okay, so here are the steps. Our sequence a sub n is this whole thing. It's n sine 1 over n squared. Okay, and we know that this thing is asymptotically the same as, so guys, sine of 1 over n squared. If this was just sine of 1 over n, yeah, let me just do it step by step. If it's just sine of 1 over n, then that part is going to be asymptotically the same as 1 over n. Just this part, sine of 1 over n and 1 over n behave the same way, okay? Now, you can replace this n with anything. You can replace it with square root of n, like that. You can replace it with n cubed. You can replace it with n squared, and that's what we want. Okay, so without having this n, without this n in front, sine of 1 over n squared is asymptotic to 1 over n squared. This is, again, just like an equation. It's like an equality, but this equality holds true in a long run. Okay, but it's just like an equation. And what can we do with equations? We can multiply an equation with the same thing. So multiply by n. So since there is an n here, I'm going to put an n here as well. Again, as easy as that. And this gives us just 1 over n. And that is our b sub n. Did you guys see how simple that was? Again, let me do it one more time. Sine of 1 over n is asymptotic to 1 over n. Well, we have sine of 1 over n squared, so we replace n with n squared. And we just multiply both sides by n. you get it? Are we good?
Yeah.
Excellent.
There's also something small someone mentioned in the chat. I think when you expand out the terms, it should be 2 sine of 1/4 and then 3 sine of 1/9.
Oh, did I mess
Yeah.
up on my expansion? Oh, there, this is an n. You're absolutely
Yeah, that was just someone who mentioned in the chat, so I'm just
Yes.
voicing their thing.
yes. I don't know why I thought of 1 over n in front. It's n. So 1 and 2 and 3 and so on. Yeah. So guess what? Our sequence compares to a harmonic sequence, to the harmonic sequence. So we can compare this series to a harmonic series. This series in a long run behaves like a harmonic series. You have to say why. It's because, step 2, because the limit as n goes to infinity of a sub n to b sub n is equal to 1. It's because of that. Do I need to show this? No, absolutely not. The book wants you to show it because they don't teach you a way to find a sub n. Book doesn't do that. They just say, hey, pick a sequence b sub n, whatever you want. So the way we pick our sequence forces this limit to be 1, and you just mention it. Don't prove it. Move on to the next step and tell what happens to the series of b sub n. Our harmonic series, divergent. Because it is the harmonic series. Done. No need to prove it. We've already proven series 1 over n to be divergent. Okay, and the conclusion. The original series diverges also by limit comparison. Okay. I didn't even do the nth term test, guys. I didn't even bother with that. Remember, I said in the beginning, if you have a series, try and do the nth term test in your head. I said that in the beginning. So when I look at this series, when I look at this sequence, I try to do the nth term test in my mind. I ask myself, what happens as n goes to infinity? Well, I immediately get indeterminate because as n goes to infinity, we get infinity, and then here we get 0. So infinity times sine of 0, that's infinity times 0. It's indeterminate. Finding the limit there is gonna consume some time. So doing the nth term test can take up so much time, and it can eventually probably be inconclusive. I didn't even bother with that because the limit comparison makes it so easy. Okay.
Professor,
Any questions? Yes.
for step 2, how is it equal to 1? Because doesn't 1 over n go to 0? So shouldn't it go to infinity? Or
Okay, well, you could try it out. You don't believe this step, do you?
I don't know if I believe it or not.
It's okay. It's all right. We'll do it for you.
Okay, thank you.
Limit as n goes to infinity, not a problem. A sub n is n sine 1 over n squared, and b sub n is 1 over n, just like that. So when n goes to infinity, well, try to simplify this thing. Just simplify. It will simplify to n squared sine of 1 over n squared. Okay, just
Okay.
yeah, multiply by the reciprocal. So this is the same as multiplying by n over 1, and it gives you that. Now, when you take the limit, this is gonna be infinity times 0, and it's indeterminate.
Okay.
Okay, it's indeterminate, so you have to write it as a fraction so you can do L'Hopital rule. How do you write it as a fraction? Remember, we can write products as fractions. I could write that as sine of 1 over n squared divided by 1 over n squared. Just divide by the reciprocal of that. And now you do L'Hopital rule. Take the derivative. If I take the derivative of sine of 1 over n squared is going to be cosine of 1 over n squared multiplied by the derivative of 1 over n squared divided by the derivative of 1 over n squared. These derivatives cancel and you just get cosine of 1 over n squared. When you do the limit of that, you get cosine of 0, and cosine of 0 is
Okay,
1.
that makes sense. Thank you.
It's 1. Yeah, I'm gonna erase all this, guys, because again, we know this limit is 1 because of the way we choose. Because of the way we choose B sub n. Okay.
Professor, I just had a really quick question on the first step regarding the n. Yeah, like I understand like how you told us the identity of like sine of 1 over n squared is asymptotically similar to like 1 over n squared, but what about the n? Do we like drop that or not consider it?
Which
or,
n? This n?
yeah.
Why I did not drop it? It's right there.
Okay, yeah, that's what I'm a little confused about. Like, why do we
So again, look, just again, pay attention to these steps, okay? Sine of 1 over n is asymptotically the same as 1 over n.
Yeah.
Okay, we know that. And then you can replace this n with anything. I can replace it with n squared. And the statement's still true. That's just a substitution. And again, this is like an equation. This is like an equation, but this equation holds true in a long run when n goes to infinity. So you can multiply both sides of this long run equation with anything you want. You can multiply by n.
Oh.
Just put an n on the left and on the right. I did not ignore that n. So you see what happened? Multiply by n.
Okay. Does that hold true for like if there's like addition? What if it was like n plus sine of n squared, 1 over n squared?
Yeah. Yes. Of
Okay.
course. Yeah. It's
Cool.
like an equation.
Okay.
An equation that is true in the long run.
Okay, thank you.
Okay. All right, good. Let's do more then. Let me just go on to the next page. These are very famous problems that I'm doing. Next one. Let's do that on the next page. I'm going from 1 to infinity of tangent inverse of n over n. And guys, for this problem, I will do both limit comparison and basic comparison. We'll do both ways. Okay, so for this example, we're going to use limit comparison test. It's the easiest. If you have the option between the two, just do limit comparison. All right. Tangent inverse function is such a good function because it is asymptotic. Jose, I never answered your question. Yeah, Jose, I guess I just did answer your question. You can use whatever test you want unless the problem asks you to specifically use a certain test. Okay, but for now we're going to use limit comparison. And I was saying tangent inverse of n it's a bounded function. It has a horizontal asymptote. Go back to section, what was it? 6.8, guys, section 6.8. We drew tangent inverse of x, tangent inverse of n, same thing, but it's again, this is a sequence. Graph of this sequence is just a subset of the graph of tangent inverse of x. This is the n-axis. Remember that tangent inverse x has a horizontal asymptote at pi over 2. Okay, and if I were to graph this sequence, n, guys, n here doesn't start at 0. I mean, this is the graph of tangent inverse of x, right? But this is a sequence, n begins with 1. So tangent inverse of 1, that would be pi over 4. Again, I'm graphing here tangent inverse function. Tangent inverse of 1 is pi over 4. Okay, so this is the first term of tangent inverse. This is what we are graphing, just tangent inverse of n. And then the sequence is just going to get closer to its horizontal asymptote like that. Okay, it just keeps going forever, getting closer to that horizontal asymptote. Okay, graph of tangent inverse of n. Let me do it in blue. Right there. Okay. So what we know about tangent inverse is that it's asymptotic to pi over 2. This behaves in the long run like pi over 2. Is that right? You understand that? Tangent inverse, when you take the limit of it, it becomes pi over 2. So it's asymptotic to pi over 2. A function that has a horizontal asymptote is asymptotic to that horizontal asymptote. Okay, that's what we get. So using limit comparison on this problem, step 1, our a sub n is tangent inverse n over n. The top is asymptotic to, again, pi over 2, and n in the bottom is just n. The leading term in the bottom is just n. Leave it. Okay, and pi over 2 over n becomes your b sub n. Very easy. So that's what you do whenever you have a tangent inverse of n. Okay, and then second step, mention the limit. Don't prove it, just mention it. Limit of a sub n to b sub n is equal to 1. Don't believe it, you can evaluate it. It's very simple. And then next step, say what happens to the summation of b sub n. Okay, so here we get the summation of b sub n. Here is pi over 2 over n. This series is nothing but pi over 2 multiple of the harmonic series. Isn't that right? Pi over 2 is a constant factor. It's just a rescaling factor. You could just pull that out of any series. It's a constant. Pull it out. And you have the harmonic series. This is divergent. This is infinity. Pi over 2 times infinity is still infinity. This is just divergent. Yeah. So it's divergent because, again, it is pi over 2 multiple of the harmonic series. Okay, and we are done. All right. The original series therefore diverges. By limit comparison test. Ahmed is asking, guys, read that question. What if you have a vertical asymptote? Will it be asymptotically the same as the vertical asymptote? Ahmed, oh, hold on a second, man. Let me turn my camera on. Let me reach through my camera and just grab you, dude. Oh. You're killing me, bro. Can someone answer his question? Okay, enough with that. Can someone answer that question? Because, yeah, why is that? Why? That's not even a valid question, Ahmed. I had to kind of exaggerate because I wanted you to remember. We can't even have a vertical asymptote. Guys, this question is a great question, actually. It's a good question, and I really wanted to exaggerate. So there is an emphasis on the answer. A series can't have a sequence that is not continuous. It's just not going to work out like that. For example, if we have this series, the series of tangent inverse, not tangent, just tangent of n over n, guys, as n goes from 1 to infinity. Imagine we have this series. Now, well, we have tangent of n, not tangent inverse. Tangent function has points of discontinuity basically at every odd multiple of pi over 2. Okay, so this question wouldn't even be valid. There is no such thing as this series, a series that has infinitely many points of discontinuity. It's just not gonna work, Ahmed. No one would ask such question. Because if you were to draw the sequence will do that. It's just gonna keep doing that, and how are you gonna find the sum? I mean, the terms go to infinity at certain locations. So yeah, these series, the sequence function is assumed to be continuous. It's continuous over the interval, so it's not gonna have vertical asymptotes. Okay, yeah, we don't worry about such questions. Okay, so one more thing. I wanted to show you guys how to do the basic comparison also on this question. Okay, so same example. But we're going to use basic comparison test, which is a little bit more difficult because we have to do, first of all, guess and then come up with an inequality. But step one, here we guess divergent. See, that is not easy. If I hadn't done the problem, if we didn't discuss the problem, then that guessing part would be difficult. Guessing divergent. I guess, again, the logic would be that tangent inverse of n as n goes to infinity, this is just acting like a line, a horizontal line. And therefore you have that times 1 over n, which is the harmonic series, therefore divergence. That would be our guess. Again, this guessing part is something we don't like with the basic comparison. Okay, so step 2. We need to find a b sub n such that what? Such that a sub n, is it supposed to be less or greater than?
Less than.
This
Less
would be-
than.
yeah.
Well, it's supposed to be less
thought it was-
than. No,
I thought it
greater.
was greater than.
Yes, greater than b sub n. See, you have to think, guys, for these problems, you really have to use your brain. Okay, and again, why is it that we choose this inequality? Because if the summation of b sub n is divergent, if it's divergent, then our series, as long as our series is greater than infinity, then that series is proven to be divergent. That's why we want a greater than. Okay. All right, so how do you get such sequence b sub n? Well, pay attention to the sequence of tangent inverse n. Tangent inverse n is between, if you notice, it's between pi over 4 and pi over 2. Look at the terms of the sequence, guys. The smallest the sequence is pi over 4. And above, it's bounded by pi over 2. It's not going to exceed pi over 2. So below, it's pi over 4. And above, and I'm going to have to erase this. Erase the equal sign. Above is pi over 2. It's like the squeeze theorem, kind of. So this is true for n. Always true for n greater or equal than 1. All right. That's the domain of the sequence. Okay, so you can take this inequality and divide by n, because our a sub n is tangent inverse n over n. So divide by n. And since n is positive, the direction of inequality does not change. We're going to get tangent inverse of n over n less than pi over 2 over n and pi over 4 over n. Okay. This is your a sub n, and you wanted a sequence b sub n that is less than this sequence, and that sequence would be pi over 2 over n. Isn't it? Yes. Pi over 2 over n. That's what you choose your b sub n to be. Is that correct? Is that what I wanted? I wanted a sequence b sub n that is smaller than. Oh, smaller than. So it would be this sequence here. Sorry. It's pi over 4 over n. See, a lot of thinking goes into it. Okay, again, this is my a sub n. A sub n is greater than this sequence here, so this sequence is going to be your b sub n. Mhm.
Wouldn't it be inverse tan of n over n?
Yes, it is. Tangent inverse n over n. Yeah, this is greater than or equal to pi over 4 over n. That's your b sub n. Okay, and again, finish the problem, guys, please. This is basically pi over 4 multiple of the harmonic series, same conclusion. It's divergent, therefore the original series is divergent. As you can see, I am so reluctant to finish the problem because, well, God created the limit comparison test. This would be a waste of time. Okay, but finish the problem, please. Okay, I want to do one more example. We haven't yet seen a case where, let's see, where these scenarios happen. The limit comparison test has 3 statements. Okay, so far we have seen this scenario. We haven't seen the next 2 scenarios. I want to do a problem where we don't get a limit of 1, or we can't get a limit of 1. And I really need you guys to pay attention. Okay, so let's say we have this series here, 1 over n, 3 to the n. Again, pay 100% of your attention to this problem, okay? So guys, a sub n, hang on one second. One second, please. Yeah, a sub n is 1 over n 3 to the n. And again, I want to use limit comparison. Okay, the question is, can I find a sequence that is asymptotically the same as this sequence? That's what we are trying to answer. Is there a sequence that is asymptotically the same as this sequence? Well, first of all, we don't have a bounded factor like tangent inverse of n. If you have tangent inverse of n, that compares to pi over 2. Cool. We don't have that. I don't have a sine of 1 over n either, because if I had a sine of 1 over n or sine of 1 over n squared, I could compare that to 1 over n or 1 over n squared. Okay, we do not have a fraction like this problem here. This fraction, I could find a sequence that is asymptotically the same as that because this fraction consists of terms. You guys hear me? It has terms. That's a term. And when it has terms, we can take the leading term, the dominant term. Okay? But our sequence here, 1 over n, 3 to the n, is none of those. On the numerator, we have a single term. In the denominator, we have a single term. a single term. So I really I cannot find a sequence that is asymptotically the same as this. I really can't. Because there is a single term on top and a single term on the bottom. And if you have a single term, then that term dominates. You understand what I'm saying? This is the only dominant term in the bottom, and this is the only dominant term on the top. Remember, terms are separated by plus and minuses. Terms are not separated by multiplication. These are factors. They are not terms. Okay? That is the thing with this problem. A sub n, because there is a single term on the numerator and denominator. If you have a single term, then where the heck would be my dominant term? Does that make sense, guys? I mean, what am I gonna do? Say this is asymptotically to 1 and the bottom is asymptotically the same as n to the 3n? What the heck? Does that make sense? If we had, let's say, instead of n times 3 to the n, if I had n plus 3 to the n, then I could take the dominant term in the bottom, which would be 3 to the n, and I could ignore n. But that's not happening here. Okay? That can happen sometimes, guys. The limit comparison works the best. Okay, the asymptotically, the limit of an to bn is 1. It works the best if you have a fraction with multiple terms on top and bottom, or a sequence that involves sine of 1 over n, or a sequence that involves tangent inverse of n. Okay, but here we can't. So yeah, I can't do anything. But that doesn't mean that the limit comparison is not going to work. All right. So what you're going to do is just choose a sequence. Choose a sequence. It could be anything reasonable. Anything reasonable. All right, so since I'll write it down. So if there are no dominant terms to be chosen, then what you do instead is choose dominant factors. Choose the dominant factor on top and bottom. Okay, they're not going to be asymptotic the same, but the problems will still work out. Okay, so what should I choose my b sub n to be? Well, top is just the 1, so there's only one factor, 1 on top. In the denominator, what factor should I choose? Yes, 3 to the n. It dominates in the bottom. It's dominant factor. Again, here the limit of a sub n to b sub n is not going to be 1. it's not, because I wasn't able to find a sequence that is asymptotically the same as this. B sub n is not going to be asymptotically the same as A sub n. So for the next step, you have to find the limit. All right, and it's okay. Find the limit. Find the limit of A sub n to B sub n. Okay, A sub n is 1/3 to the n divided by B sub n is 1/3 to the n. Simplify. This limit is typically easy to calculate. Simplify, you get 1/n. Yes, that's what it simplifies to, and the limit of that is 0. Okay, obviously, it's not 1 because A n and B sub n are not behaving the same way. Okay, why is that? Well, it's because this sequence diminishes faster. These are both going to 0. They both go to 0. That's correct. But they don't go to 0 at the same rate. They don't go to 0 with the same rate of change. This sequence is going to 0 faster. That's what this is saying. That's why they're not asymptotically the same. Okay, so that was step 2, guys, by the way. Step 2. And then step 3, just tell what happens to the series of B sub n. B sub n is 1/3 to the n. Yeah, what happens to this, guys? Is this convergent or divergent? That's 1/3, the whole thing to the n.
Convergent.
Convergent.
Converges. Justify, you say, because it is a geometric series with absolute value of r less than 1. Done. Okay. And then look at what limit comparison test gives you, tells you. If I go back to the statements, we are looking at the second scenario, the second statement of limit comparison. It says if the limit of the ratio is 0 and the summation of B sub n converges, then the summation of A sub n must also converge. Yeah, it's this statement right here. And that happened exactly. Okay, so limit of ratio is 0 and the summation of B sub n converges, therefore. Whenever n3 to the n converges by limit comparison test. Again, the reason for it, try to understand why. Don't just say, okay, yeah, this is true because the theorem says so. Try and understand the reason behind all of this. So this is saying that since this limit is 0, okay, then what's going on here? Then, is that right? The limit is 0. Yes, so since the limit is 0, then we have which series is going to 0 faster? Let me see. Hold on, what's the question? Would you accept shortening geometric? That's fine. That is totally fine. Yes, you can. You wanna abbreviate things. Say geo instead of writing geometric, that would be totally fine. Okay, so guys, explain to me why this is true. What is going on here? So here, since this limit is 0, then B sub n takes over. B sub n is, well, what you get basically is that the summation of A sub n, again, is less than the summation of B sub n. And we know that this is convergent, so it's equal to some finite number. Therefore, the original series is less than something finite, therefore it's convergent. Okay, but not every test. So every test has got some disadvantages. Okay, so the disadvantage of the integral test is that this is a lot. It's huge. We can't integrate every function. It's really tough to find integrals. The disadvantage of basic comparison is guessing, first of all, and then second, coming up with the proper inequality. The disadvantage of limit comparison, it has less disadvantage, is that it is good if you can find a sequence that behaves like your sequence in the long run. Okay, and that happens if your sequence consists of terms, not factors. But, well, someone came up with a test for when your sequence or the terms of the series consist of factors. See that for this problem, we had to think a little bit. We had to think because the sequence has factors. Okay, there's a test, again, that is designed for that. And that test is called the ratio test. And the ratio test, let me see what section that is in. Give me 1 second. Oh, we're at 9:21, guys. We'll cover that tomorrow. We'll cover the ratio test tomorrow. Any questions before you go? Yes, I think it's on 11.6. We are done with this section. We are done with 11.4. We'll begin 11.6 tomorrow, and then 11.5 will be covered after 11.6. Okay? But I'll see you guys tomorrow.
Thank you.
All right, have a
Professor.
great day.
Professor, what time are your office hours tomorrow? I can't make it to your normal ones today.
Tomorrow is Wednesday.
It's a math lab day, right?
Yeah, I have math lab hours at 3:30.
Okay, but they'll just put me into your class, right?
Yeah, just log on, just Google SMC Math Lab.
Yeah.
And just join their session. They'll put you out and they'll put you with me in the breakout room.
Sounds good. And are you going to post the little quiz or extra credit thing you said?
Yes, I will post something for sure.
Okay, sounds good. See you tomorrow. Thank you.
Bye.